Okay, external force convection. So today's topic is about flow across cylinder and sphere. Objective of this study, you should be able to evaluate the heat transfer coefficient associated with flow over a cylinder and sphere. Okay, flow across cylinder and spheres is frequently encountered in many heat transfer systems. For example, shell and tube heat exchanger, and then second is spin fin heat sinks for electronic cooling. For both of these equipments are using heat transfer mechanism. For example, conduction and convection, for example. And then in order for you to determine the Reynolds number for cylinder and sphere, you have to change the characteristic length from a Reynolds number equation into external diameter. Okay, I will explain to you after this. So the critical Reynolds number for flow across a cylinder and sphere is about 2 times 10 to the power of 5. So let's take a look at the equation for Reynolds number. So previously, you know that the Reynolds number equation for a flat plate. So I will write down here. Flat plate is Reynolds number equal to rho density times with velocity times with x divided by mu. Okay, that is the first equation. Equation for Reynolds number, or we can change it into another form. So Reynolds number is equal to velocity times with x divided by kinematic viscosity. In heat transfer, Reynolds number equation is actually Reynolds number equal to rho v LC divided by mu, or Reynolds number equal to V times with LC divided by kinematic viscosity. So LC is characteristic length. For a circular or sphere, okay, circular or sphere, so we have to change LC into external diameter. So the equation becomes Reynolds number L equal to rho times with velocity times with diameter out divided by mu, or Reynolds number L equal to V d out divided by kinematic viscosity. So you have to remember that diameter used in this equation is diameter out. So when you draw a sphere or a cylinder, let's draw this first. Okay, so we know that sphere or cylinder have thickness. So this is thickness of sphere or cylinder. So thickness. So you have to remember that for a circular or sphere, it will have diameter inside and diameter outside. So in this chapter, we are dealing with external force convection. Therefore, diameter that will be replaced in the characteristic length will be diameter outside. So the fluid that flows is outside of the cylinder or sphere. So you have to calculate D out. Okay, for example, in the equation, in the question, they give inside diameter is 10 centimeter. Okay, the thickness of cylinder maybe 3 centimeter. So you have to remember that this 3 centimeter only represent this thickness. In order for you to determine what is the diameter outside, you have to times with 2. Therefore, if you want to find diameter out, you have to 10 centimeter. You have to sum up 10 centimeter with 2 times with 3 centimeter. Okay, so the out will be 10 centimeter times with 6 centimeter. So it will be 16 centimeter for diameter outside. Okay, so why we have to times with 2? Because thickness, we have thickness. So the thickness is wrapped around the cylinder. So we have thickness out of the cylinder. Okay, therefore we have to times with 2 because here we have thickness and here we have thickness. So in order for you to calculate the diameter from here to here, you have to add 3 centimeter, 3 centimeter and 10 centimeter in order for you to get 16 centimeter. So that is Reynolds number equation for a cylinder and sphere. So at very low upstream, take a look at this figure. At very low upstream velocity, normally Reynolds number below than 1, the fluid completely wraps around the cylinder and the two arms of the fluid meet on the rear side of the cylinder in an orderly manner. So at low velocity, these flows will wrap around this tube. So this is tube, this is cross sections of a tube. So the fluid that flows will wrap around these tubes. Okay, thus the fluid follows the curvature of the cylinder. But what happened when at high velocity, some of this flow, previously at low velocity, it will wrap around this tube. At high velocity, it will detach from the tube surface. So it will form a separation region. So this is what we call a separation region or wake region. Okay. So that is how the fluid flows on over a cylinder or a sphere. So there are so many equations available. There are so many available literatures that shows how to calculate the heat transfer coefficient. But for this subject, we will use this equation for cylinder and sphere by Churchill and Bernstein and Whittaker. So Churchill and Bernstein we will use for a cylinder, and flow over sphere by Whittaker. Okay, so here we have Nusselt number. Previously we know that Nusselt number for flat plate, if we want to equate in order for you to determine what is the heat transfer coefficient, you have to equate with HL over K. But now the equation L will change into diameter. Okay. So diameter here is diameter outside. So you have to equate with this equation in order for you to determine what is the heat transfer coefficient for a cylinder. Okay. So the properties are evaluated at flame temperature. So if properties for cylinder, will be evaluated at fluid properties, okay, at film temperature. So you have to calculate what is the film temperature. Tf equal to T infinity is fluid temperature plus with T surface, Ts is T surface divided by 2. Okay, and then you will refer in your books table appendix, so you find the fluid properties at T film. Okay, and you need to substitute all the value and plug in into this equation. So sometimes all these fluid properties will be given in your question. Okay, normally will be given in your question, but if in the question requires you to find the fluid properties in order for you to determine what is the Nusselt number for a cylinder, you have to determine it by using a fluid properties, by using a film temperature. So for the Nusselt number sphere, we will use this equation. You have to remember this equation is slightly different with this equation in terms of the properties evaluated. Okay, all the properties inside of this Nusselt number for a sphere will be evaluated at T infinity, except for mu s. So this mu s will be evaluated at T surface. Okay, for example, if you have sphere and then the fluid outside, so T infinity is 100 degrees Celsius. And then T surface is at 30 degrees Celsius. So all the properties will be evaluated at 100 degrees Celsius, except for mu s that will be evaluated at 30 degrees Celsius. Okay, if you substitute into this equation, and then you will get the Nusselt number for a sphere. Therefore, you need to equate with Hd over K in order for you to determine what is heat transfer coefficient. Okay, again, this diameter is represent for diameter outside. So this is diameter outside. Okay. So how to calculate? Very easy compared to a flat plate. So first step is to calculate what is Reynolds number. So you know that Reynolds number is rho Vd outside divided by mu, or you will use Reynolds number L equal to V D outside divided by V. So next is, before this, you know there are two equations, cylinder and sphere. If your equation is cylinder, then in the question mentioned about the cylinder geometry, therefore you will use a cylinder equation. So in here, you have to find what is Nusselt number for cylinder or Nusselt number for a sphere. So depends on question. Depends on question. Next, you have to equate with Nusselt number equal to Hd over K in order for you to determine what is heat transfer coefficient for that question. So normally you are required to find what is heat transfer coefficient. After you get the heat transfer coefficient, then you can substitute into a rate of heat transfer. If the question asks you to find what is the rate of heat transfer. Okay. So the step is simpler than flat plate. Okay, this is example of if the question asks you to find what is the rate of heat transfer. Okay, a more compact correlation for flow across a cylinder will be determined by this correlation. Actually, in your question, normally we will use these two types of equation, okay, cylinder or sphere. More compact correlation is summarized in this table. As you can see, there are circular and non-circular shape. Okay, for example, if we are talking about circle, so you have to determine what is the fluid, either it is a gas or liquid, and then a range of Reynolds number. You cannot simply take this Nusselt number as your equation to determine Nusselt number for that equation, that question. You have to calculate what is the Reynolds number and then try to find where is the range of your Reynolds number in this table. So if your Reynolds number range is 4,000 to 40,000, then you have to use this equation. Okay, extract this info and then plug in all the values needed in order for you to get what is Nusselt number. Okay, this is for circular and non-circular, a compact correlation. But normally we will use these two equations, Nusselt number cylinder and Nusselt number sphere. Okay.